So this is me, I'm Simon, welcome. It's my first time in Riga properly. I've flown through a bit here before but never got out of the airport, so this is fantastic. It's quite cold though. I live in this place here, Jersey. Can you see it? No, it's far, far too small. It's a tiny island in the English Channel. If this was interactive like a big iPad, we could pinch to zoom in, get a bit closer, a bit bigger, still fairly small. We could pinch to zoom in one more time, and there we see Jersey. So it's a small island, it's 15 kilometers by 8 or 9 kilometers, surrounded by sea. Why do I live there? It's a nice place. You might be asking how much IT work happens in Jersey. Come talk to me in the coffee break. Most of my career has been spent building software systems, mostly in Java, and I actually worked in London for about 12 years. And I moved back to Jersey 6 years ago just because it's a nice place to live. But over the past few years, I've been jetting around the world and really helping teams understand what software architecture is all about. Now, you might be thinking, why on earth does the Software Craftsmanship Conference open with a talk about software architecture? All should be revealed. My whole picture is really that architecture needs to be much more accessible to us as software developers. So there's lots and lots of material out there about software architecture, but when I was moving into my first architecture role, I didn't really understand how that stuff related to my day-to-day job. And that's really the problem I want to solve here. So how do I solve this problem? Well, I just wrote some different books. So I've written a couple of books about software architecture, and I'm the creator of this thing here called Structurizer. This is Software Architecture Diagrams as a Service, which has an unfortunate acronym of SADAS, which is kind of ironic because, well, it's not ironic, because I basically just talk about diagrams all the time, and this talk is no exception, of course. And really, this talk is about the intersection between architecture and code, the intersection between architecture and craftsmanship, if you like. But before we get to that point, we have to look at the tension between these two things. So we often treat architecture and code as being different things. Why is this? Well, let's go back to pictures. So imagine we want to draw a diagram. We want to draw a diagram to describe something about the system that we're working with. Let's imagine you inherit a code base. Let's say it's a couple of million lines of Java code, C# code, whatever. And let's say this code base is made up of 100,000 classes. If you are asked to draw a picture to describe that code base, would you draw a picture with 100,000 boxes on? No, it's a ridiculous idea, isn't it? There's far, far too much detail there. So we use abstraction. We use abstraction to manage complexity, essentially. So rather than drawing those 100,000 classes, we group things together. And we draw those bigger things on our diagrams. And we have names for these bigger things. They're called modules or services or components or subsystems. And the whole point of abstractions is that it allows us to reason about and understand a big complex software system. So we have a diagram. It shows our modules, our components, our layers, our services. And of course, there are lots and lots of different ways to do this. So this is an excerpt from Philip Critchton's 4+1 model. And it says, to describe a software architecture, we use a model composed of multiple views or perspectives. This is Philip Critchton's 4+1 model. So we have some sort of logical view of our system, showing our modules, our components, our services. We have some sort of development view, which talks more about the code and how the code is organized. We have some sort of process view that talks about concurrency, for example. And we have an infrastructure view, a physical view. And all of these things are tied together by a set of use cases, or whatever you want to call them these days. This is not the only option, of course. There are lots and lots of other ways we can describe architecture. There are lots of view catalogs, they're called. And the problem with these view catalogs is that they're not consistent. Every view catalog has their own way of describing these things. And it's the naming that confuses people. So in one view catalog, you'll have a design view. In another one, that same thing will be called the logical view or the development view. And the naming is not consistent between these different view catalogs. Naming aside for a second, what you will discover very quickly is that the logical view of a software system, in terms of its modules, components, services, and layers, is usually very, very separate from the development view. So the code-oriented stuff. And this makes my head hurt. Brain freeze. Have you heard the term brain freeze before? It's when you eat ice cream really quick, and it makes your head hurt. Now, there are a couple of ways you can prevent brain freeze. One is to drink coffee before eating ice cream very fast. That's just a workaround. The other option is to just not eat ice cream. Try telling this to my kids. It doesn't work. Or we could cheat. So if we want to describe our software system and we want to draw some pictures, we could just cheat. How do we cheat? Well, let's go ask Google. Google, what does the software architecture picture look like? It gives you stuff like this. Yeah, you've seen this before? It's just page after page after page of basically pretty block diagrams. And ultimately, we get to stuff like this. And whenever I go and see organizations around the world, this is what they have in their documentation sets. And some of these diagrams make absolutely no sense at all, but they look nice on a PowerPoint presentation. They're architecture diagrams. And this is what we need to get away from. You might be asking, well, where's the unified modeling language in all of this? Where's UML? Well, who cares about UML here? Who uses UML here? 1, 2, 3, 4. That's it. And some of those hands were very tentative. Yeah, you're afraid of using UML. I've asked this question all around the world, and apart from Germany, for some reason I don't understand yet, most people don't seem to use UML. So let's put all of that stuff aside. What is it we're trying to do with these diagrams of our systems? Well, if I'm doing an upfront design exercise, this is really the question I want to address. Is this what we think we're going to build? And if I'm retrospectively drawing diagrams from an existing code base, it's this question. Right, is this what we have actually built? The problem with all of this stuff is we basically lack a consistent way to do this. Within our industry, we don't have a consistent set of language or terminology to describe software. And I'll give you a really, really simple example. Think about the word component. How many times have you heard people using the word component for very, very different things? For some people, a component is an application which is part of a larger system. For other people, a component is something running inside that application. The same word, very, very different levels of abstraction. So how do I do this? Well, for me, a software system is made up of a bunch of containers. A container is just something that executes code or hosts data. In real terms, it's a mobile app, it's a web app, it's a database, it's a file system, it's a batch process, whatever. If we zoom into those containers, for me, they're made up of components. So I'm going to use the word component to mean something that runs inside another process, essentially. It's a massively overloaded term, but all a component is basically a bunch of related stuff with hopefully a nice clean interface on top. And because I mostly deal with Java systems, my components are made up of classes. And that's it. It's just a really, really simple hierarchical tree structure to describe the static structure of a software system. Of course, if you're doing functional stuff, maybe it's module and function. If you're doing JavaScript, maybe it's component and function. If you're doing database technologies, maybe it's component and store procedure function. So that you might have to adapt the static structures to suit the technology that you're working with. And really, this is a static structure first approach. And what I want to do is I want to figure out how to describe a software system from the very highest level, the system as a single box, down to essentially the code and a couple of steps in between. And once you understand the static structure of what you're building, you can weave in the other views really easily around it. So for example, if you want to show how a user story or a use case is implemented by a sequence diagram, well, that's just a sequence diagram showing collaborations between things in your static model. Things like components, for example. Your deployment model is basically a mapping between your containers and your infrastructure. So again, understanding the static structure opens up lots and lots of other doors for you. Why do I do this kind of static structure first approach? Because I think software architecture is important for us as developers. I actually think we as developers are the most important stakeholders of software architecture. So that's why I want to bring architecture back down to earth again and make sure it's linked up to the code somewhere. Now, the reason I did my silly zoom in thing at the start wasn't because I was trying to be funny. It was because I want to plant the seed about maps, and that's essentially what I'm trying to do here. When I'm describing a software system, I want to create a set of maps that you can use to navigate your code base. So if you open up your mapping application like Google Maps on your smartphone and you do a search for Jersey, you typically get this bottom picture by default. So Google Maps will zoom straight into Jersey and show you, it basically fills the screen with Jersey. And this is great if you want to know what's inside Jersey and what the place names are, but if you've never heard of it, it's totally useless. So the first thing you have to do is pinch to zoom out a few levels to get to the map of Europe. when I'm drawing pictures of my system, I want to do the same sort of thing. So sometimes I want a low-level view of my system components, and at other times I want to zoom up to see the system in its entirety. In other words, how the system fits into the rest of the environment. So let me give some quick examples of these diagrams. When I moved back to Jersey 6 years ago, I wanted to find other tech people. So I created this thing here called techtribes.je. It's just a basic content aggregator for the local tech industry. It lists local people, businesses, blog posts, tweets, events, and that sort of thing. And this is a context diagram showing my tech tribe system. So there are various types of users at the top. If you go to the site now, you'll be an anonymous user. I can sign in with my Twitter ID and manage my user profile, and there's a top secret admin user. And these are my systems I depend on along the bottom. So we're pulling data from Twitter, we're subscribing to blogs, and we're pulling information from GitHub. It's just a nice, simple starting point picture. It shows the system in the middle with other stuff around it. If this was interactive, and we were interested in how the tech tribe system was made up, we could pinch to zoom in, and we get level 2, and this is the containers diagram. It still has people at the top and systems at the bottom. And basically all I've done is I've exploded that monkey to show that it's made up of a web application at the top. That's a single point of access for the users. There's a content updater at the bottom. It's a standalone Java process. It's a thing that reaches out to Twitter, GitHub, blogs, and pulls the data back. And the data is being stored somewhere in those middle trio of boxes. Blog posts, and a file system in the middle. So again, it's just a very high-level diagram. It's showing you something about the static structure. This diagram does not show you anything about clustering or deployment or anything like that. That's a separate view. Again, if this was interactive, we could pinch to zoom in on this little content updater thing, and we could see inside it. And this is a component diagram for the content updater. So the content updater is this thing here. It talks to the systems in the outside world, and it talks to these other containers at the top. And basically, this is just a simple breakdown of the components that make up my content updater. You can see in the middle there's a scheduled task, a Spring scheduled task. It uses a bunch of connectors to connect to the outside world, and then it uses a bunch of other components to store data. That's it. If we were interested in the component implementation details of this Twitter component, and the Twitter component basically, all it does is it allows you to store tweets into a Mongo data store and get back out again. We could pinch to zoom into the tweets component, and we get something different. So this is level 4. This is a class diagram showing the component implementation, but there's something weird about it. On the component diagram, I had one box. It said tweet component. It's not one box anymore, is it? It looks like some classes in some packages. Where's my component gone? It's disappeared. I have this nice vision of a component on my diagram, but it turns out that doesn't really exist in the code. In the code, it's a collection of classes and interfaces across a layered architecture. That's what this diagram is showing you. So my component diagram is lying to you. It's not telling the whole truth. And this is a really good example of this mismatch between the architecture world and the code. And it basically comes back to this question: does your code reflect the abstractions that you think about, the abstractions that you describe, the abstractions that you draw on your diagrams? And I think the answer in many cases is no. And a lot of this boils down to this. It's a clash between how we organize our code versus the way we describe it from an architecture perspective. Have you seen this before? You have a bunch of really nice diagrams on your wiki or on your wall, and they're just lying to you. They're out of date. They don't tell you the truth. They don't match the code. Yeah? This is what we call the model code gap. There's a fantastic book about software architecture called Just Enough Software Architecture by George Fairbanks. And he calls this the model code gap. Very simply, when we're having an architecture discussion, we're using terms like modules or services or components. We don't have those same concepts in our code. So quick show of hands, who's a Java developer here? It's a good bunch of people. C#? It's a good bunch of people. So in object-oriented languages like Java and C#, is there a component keyword? No. You can't type public component X, can you? There's no service keyword. What about layers? How do we create layers in our code bases? Well, namespaces or packages, there's no layer keyword. It's the model code gap. There's a difference between the constructs that we use. I've traced this back to 1995. This was a paper published back in 1995. It basically says the same thing. If we automatically generate a diagram from a code base, it's super accurate. But if you compare that diagram to what an engineer would draw on a whiteboard, it's totally different. Again, the constructs, the mental model we have of our system is different. Why? Because although we think in terms of components, we don't write components in our code. We normally write a bunch of classes in a number of layers. So here's a typical example. Imagine we're building a web application. And we're going to use a web MVC framework. We're going to break it down into a bunch of layers, potentially. You know, a controller layer for web app controllers, some sort of business or services layer in the middle, and some sort of data access layer at the bottom. Have you seen this before? Fairly traditional, standard way of approaching web application design. Why do we do this? Well, the books tell us to. So this is a diagram I stole from a Spring book. It basically says if you're building a Spring MVC application, organize your code like this. You turn the page, it tells you why. Separation concerns, blah, blah, blah. You download some sample projects off the web. You load them into your IDE. That structure is created for you. Look, there's a service package and a domain package and a web package and a repository package. You go on to Stack Overflow. I'm building a web app. How do I organize my code? Somebody will say, you should do this. Layers. Same with the .NET world. You download some sample code. Layers. And this is a great starting point. So you download these sample projects. You add your first feature in this way, and then you add more features, and you just keep going. And eventually your system becomes larger and larger and larger, but it just follows the same pattern. So why do we do these types of layered architectures? Well, a lot of it is around separation concerns. So if I'm writing some business logic code, I don't really care where my data comes from, and I don't care how people use it. If I'm writing the controller layer, I don't really care where my data comes from. I just want to, deal with the interaction stuff. And if I'm writing the DAOs, I don't really care how people are using my data. So it's all about separation of concerns. And we start out with this nice, strict, layered approach. And we say things like, the controllers will only talk to the services, and the services will only talk to the repositories. And we have feature set A, and feature set B, and feature set C. And it's all nice and clean. And then we get a change request, and somebody says, feature set C, can it use a bit of B as well? And you're like, yeah, sure, no problem. And there's a number of ways you can do this. And we've all done it. What's the problem with languages like Java? Well, in Java, what we normally do is we create a package per layer. So we have a package for controllers, a package for services, a package for repository things. In order for the services to call the repositories, they're in a different package, so therefore the repositories have to be public. If the repositories are public, they can be called from anywhere. And the problem is we don't put enough discipline into our teams to stop that happening. And that's why our nice layered code bases sometimes turn into these horrible big balls of mud. Now, you might say, well, we don't do layered architectures anymore because we're using hexagons and onions. And guess what? That's just a layered architecture as well, drawn differently. Should we consider layers as harmful things? I don't think they're harmful. I think we can misuse layers, certainly, but I'm not sure they're harmful. Do we know why we're doing this, though? You've heard of cargo cult programming? Just blindly doing stuff because we think we should? Well, maybe layering is another cargo cult. Now, why do we do layering? Well, separation concerns, but why do we do layering? What's the real benefit of organizing our code base by layers? Are the layers actually important here? Should layering be the primary way that we organize our code base? Or should it be something else? Now, of course, Uncle Bob Martin's been saying this for years. He says, don't do stuff by layers because it's dumb. And that's why all applications look the same. If you open up the code into an IDE, every application basically looks the same. It's a top level set of folders, controllers, services, repositories. And he has this blog post called Screaming Architecture. And he says, if you look at a set of building blueprints for a house, it screams house at you. If you look at the set of blueprints for this library, it's going to say this is a library. If you look at most apps, they're all the same. And that's wrong. Martin Fowler, back in the summer, posted something on his Blicky basically saying the same sort of thing. He says, this whole layered approach is great for small apps. But once you get any sort of size and complexity, you need to start thinking about modularizing inside your layers. And he says, yeah, there's another way to do this. We could do a package by feature approach instead. So rather than by packaging our code horizontally, we package vertically. What does vertically mean? Bounded context, aggregate root, feature set. There's a number of different ways we can do this. And essentially, it's breaking our code up differently. So maybe we have one package per entire slice through our system. So a slice for customers, a slice for orders, for example. Does this solve the problem of creating clean code bases? No. It's just a different way to organize the code. Because if we have feature set C, and it needs bits of B, well, we have the same problem again. We need to start making stuff here public so it can be accessible from the outside world. This also doesn't solve the problem of our diagrams matching our code, because sometimes, as I said, we think in terms of modules or components, but there's no way to see these modules or components in our code base. And the abstractions on the diagram should reflect the code. That's all this is about. So this begs the question, how do we fix this problem? Right? How do we fix this problem? And the answer is very, very simple. We use an architecturally evident coding style. An architecturally evident coding style is basically dropping hints and metadata into your code base so that your code reflects the abstractions that you think about. Who thinks they do this explicitly and consciously? 1.5. When you read this stuff in the book, it makes perfect sense. You're like, obviously, this is what we should do. But it's not a technique that's really caught on mainstream. Now, there are lots of simple ways to achieve this goal. It's simply things like naming conventions. So if I have something on my diagram called a tweet component, I want something in the code called tweet component. I want the names to match. Maybe it's about namespacing and packaging. So maybe I create a namespace or a package to wrap up a component. Maybe it's about adding machine-readable metadata, attributes, annotations, that sort of thing. If you're using a module system, like Maven modules or OSGI or in the future Java 9, maybe you say one module equals a component, so you've got a nice simple way to do that. JavaScript is just horrible. But thankfully, ECMAScript 6 is getting module support, so hopefully that will fix it. And also microservices. Microservices is actually a really nice example of an architecturally evident coding style. If we were to take somebody's microservices architecture and draw a picture, it's probably going to be a bunch of boxes representing services with interactions between the services. If I look in the code, I can probably find those services really easily. There's a nice one-to-one mapping between the concepts. So again, how do I do this? Well, what I do now is I take a kind of package by component approach. And what I really want to do is create a namespace or a package around my components, around the entirety of the internals of my components. And in real terms, this is how I refactored my code base so that my code reflected my diagram. So this is what I had on the left, and it basically shows a layered architecture. So there was a services layer and a data access layer, a repository layer. And I had a tweet service with an implementation and a tweet DAO with a Mongo implementation. That was my layered architecture. And I did this really simple refactoring where I created one namespace, one package for the entirety of my tweet component. I took the interface and I renamed it to be tweet component, so now the names match. The default tweet service was horribly named, so I've renamed it to tweet component impl, which is also horribly named, but I've made it package protected. So in Java terms, this means it cannot be seen from outside that package. It's just an implementation detail. And my MongoDB tweets DAO has been moved across, unchanged, but made package protected. And actually, I've hardwired those two things together because it's just an implementation detail. And I've deleted the interface. And that's it. It's just a really, really simple example of an architecturally evident coding style. Public interface, package protected implementation details, one box in the code, in this case a package, represents one box in the diagram. Here is the code, zoomed in. So this is my code here. You can see all my files sit in a single namespace, single package. And I've also added some extra metadata to my code. I've got my own custom @components annotation. So now if we go back to the component diagram, and we select the tweets component, and we pinch to zoom in, hooray, we have a nice clean mapping. So it's now easier to navigate my code base. And all I'm trying to do here is very simply think about modularity again. So I'm trying to get modularity back into my code base. And I'm trying to get modularity into my code base at a slightly higher level than just a bunch of classes and layers. If you take this sort of approach, you'll very, very quickly work out there are a bunch of decisions you need to make. Stuff like, well, where do we put our domain classes and shared code and things like this? Well, it's up to you. You could put the domain classes next to the components, or you could have a separate bag of domain classes. There are two approaches here. They have advantages and disadvantages. Things like shared code and utils. You know, if you have an abstract component base class, where do you put that? Well, just have a bunch of shared stuff. Who cares? But all of these things should be conscious decisions. We shouldn't just cargo cult stuff, because that's how we see someone else doing it on the web. I'm going to talk about testing as well now, because there's lots of talks about testing at a software craftsmanship conference. So I should talk about testing too. Has anybody seen this paper? If you've not seen this paper, I recommend you go take a look. It's by Jim Kaplan. It's quite controversial. The title being, Why Most Unit Testing is Waste. You won't agree with a lot of stuff in this paper. I can probably guarantee you that much. I don't agree with much stuff in this paper, but it does make some really interesting points if you're not too furious when you're reading it. Stuff like this at the top. So if we look back 10 or 15 years, why did we start doing all of this mocking stuff? Well, imagine we're writing some code, it talks to a database. If I want to test the code independently of the database, I need to mock out the database. So this is basically what gave rise to, things like service layers, data access layers. If you want to unit test your services, you provide a mock implementation of your DAOs in memory, runs really fast, blah, blah, blah. One of the reasons we did that historically was performance. So these database tests were very, very intensive. They were very hard to set up. They were very slow. Fast forward back to 2015. I have a nice shiny MacBook here. It's got 16 gigabytes of RAM, half terabytes flash drive or something. It's pretty quick. Plus we have Vagrant, Docker, etc., etc. So spinning up a database environment very quickly and running some real database tests is now something we can do on modern hardware. The Rails guy jumped on this. He's like, yeah, don't let your tests drive your design. Now, I'm not going to talk about TDD because I won't leave Riga alive. But if you read the words behind this blog post, he's basically saying he's seen lots of systems where the design has been corrupted because people have introduced all these funny places to insert mocks. And so you've kind of decomposed your code base into lots of small things interacting. If anybody here has worked on a big enterprise Java Spring application where everything is wired into everything else, you will have also seen this. It's just, there are just too many moving parts. And maybe that's a bad thing. So when we talk about organizing code, I've talked about packaging our code by a layer or feature or component. And this is essentially how we organize our code, of course. We're organizing our code by layer or feature or component. Why don't we have the same discussion about tests? Why don't we have an open conversation about how we test our code, whether it's by layer or feature or component. And maybe the way we organize our code provides us some other opportunities to test our code. For those of you with a sharp eye, you'll notice that when I did my refactoring, I killed off this data access object interface. Right, there are 4 boxes here, there are 3 here. Why did I kill that interface off? In Java, you cannot have a non-public interface. Actually, that's not strictly true. In Java, you can have a non-public interface, but the methods are still public. It's this really weird thing they created in the language spec. This is an implementation detail. So my Mongo data access object is an implementation detail of my tweet component. So I've taken a conscious decision here to not be able to swap that out with an interface. I don't need an interface. So this component still has a layered architecture, but the layers are inside my component. And I can still swap out from Mongo to another data store just by changing this one class. But the question becomes, how do I test this on its own? So how do I test my tweet component impl without connecting to a real database? And the answer is, don't do unit testing on it. Now, I'm not going to stand here at a craftsmanship conference and say, don't do unit testing, because that's really, really stupid. But I think, again, testing is potentially a cargo cult. I think we're blindly applying the same ways, the same mechanisms for testing, and we're not questioning why we're doing this. So why do we mock everything out at a very, very low level so we can write fast-running unit tests? Why? What benefit does that give you? So I'm going to say this instead. Instead of blindly unit testing everything, why don't we take a more thoughtful and balanced approach to how we test our code? And maybe there are other tests we can write at higher levels of abstraction that make more sense, that allow us to write fewer lines of test code for a higher degree of coverage. Now, I'm not going to write that on the slide because somebody will say, at the DevTurnity conference, Simon Brown said, if we write one test throughout our entire system, we only need one test. User interface all the way through to the database. No, I'm not saying that at all, because that's also really, really dumb. But this is the traditional testing pyramid we always see. We have a number of very fast-running unit tests. We have a bunch of slower, probably broken integration tests. These are things that after a long weekend, you come in on a Monday morning, it's broken, you just ignore them or delete them. With a to-do on the board that says reintegrate the integration test, never happens. And if you're really lucky, and I mean really lucky, you get some UI and functional systems tests on top. What is a unit? When we talk about unit testing, what's a unit? For some people, a unit is an individual method or a class. For others, a unit is a feature, a slice of behavior. Right, why can't we agree on what a unit is? What's an integration test testing? Well, it's integrating units, obviously. But if we don't know what a unit is, well, now we're stuck. I think most people's interpretation of an integration test is, I write some code that talks to a database, and that's the integration test with the database, or the integration test with a third-party service. And I don't think these names also make much sense. But again, we're just blindly applying them. We're blindly using them day to day. So I think maybe we should have something that's more aligned with the architecture. An architecturally aligned style of testing. I still want to have a bunch of very fast-running, low-level tests. But I'm going to say they are class-focused tests. They're testing individual methods, individual classes. And we're mocking out dependencies as far as possible. That's your fast-running unit tests. But I'm going to call them class tests because I'm writing Java stuff at the class level. My integration tests, if I organize my code base by components, well, they're really just component tests, aren't they? This is actually how I test my tweet component. I spin up Mongo, I throw some data in, and I test my tweet component through the public interface. And it's really, really easy to do. Now, there are some caveats. Testing exceptions is hard, but that's a conscious decision I've made. If my tweet component was actually talking to the outside world, or sending an email or sending some sort of asynchronous message, then yeah, a component test is really hard to do. So we need to come back down to this level and make sure we have a way to mock out those external dependencies. But again, I'm taking a thoughtful and balanced approach to my testing so that I can get the best set of tests for the minimum amount of code I'm writing. If anyone's doing a microservices style environment, I'm pretty much going to guarantee you've got some service level tests. It's the same thing. You're testing your service through the public interface. And you might also have some internal lower level tests. And yeah, I still want some end-to-end tests, some system tests. The tests through the UI all the way back down to my database, for example. The names of these things, class tests, component tests, system tests, match the static structure. System made up of containers, container contains components, components made up of classes. If we're adopting that approach, that language, that terminology to describe our system, why don't our tests match? Why don't we line all of these things up? And that's basically what I'm trying to get to here. I think there should be a much stronger alignment between the way we think about our systems from an architecture perspective, the way the code is organized, and the way the code is tested. All these things need to match. Ideally with a standard set of terminology, a standard set of constructs that we use in all of these different areas. I think that's really, really important. Why? Ultimately, maintainability. Maintainability is related to the number of public things you have, the number of dependencies you have, the number of microservices you have. The more moving parts you have, the less maintainable your systems tend to be. You've probably seen this. It's also hard to reason about these systems because there are so many moving parts. And actually, if you want agility, and this is something we're always talking about, if you want agility, well, that's what a good architecture gets you. A good architecture gives you agility. But this is not something you get for free, of course. You have to put some conscious effort in. And this raises an interesting question. Well, what style of architecture do I build to give me agility? And it depends how much agility you need. And we talk about non-functional requirements in architecture. We talk about quality attributes. Let's just make agility one of these things too. So we use the amount of agility that we need as a driver to determine how much architecture we do, what style of architecture we create. And of course, there are different ways to do this. On the one hand, we have this monolithic approach. We bundle up all of our features into one thing, one deployable thing. We've been doing this for ages. We know how to do it. We've got tooling to support refactoring in a monolith. If you don't look after your monoliths, you get that horrible big ball of mud, though. Also, if you want to make that very small one-line code change, you have to redeploy your whole monolith. It's 2015. You must have heard microservices. Everybody's talking about microservices. And this is a different architectural approach. Instead of bundling all of your features into one thing, you have a bunch of things all running independently. Small services doing one thing and doing one thing well. This gives you lots of benefits around agility and scalability. You can build your services in different languages. You can version them separately. You can have different teams owning services. This is a nice approach for a certain category of problems. The downside, of course, is complexity. You have a bunch more moving parts here. You're shifting the complexity out into the integration layer. If you look at all the software conferences today, this year, it's always those are great or those are even better. And nobody ever talks about the middle ground. And it's nuts. Because in the IT world, we always flip-flop from one end to the other, from one extreme to the other. And of course, there is a spectrum of approaches here. We can still build a monolithic system with a nice modular code base. This is just all good, old-fashioned component-based design. And that's really what I'm trying to get to. Let's think about how we're building our systems. Let's not blindly layer everything. Let's think about modularization. Let's think about modularity. Let's think about creating nice, clean code bases that are easy to navigate and maintain and fix and enhance and work with. And if you want to do the microservices thing, sure. Right, but a nice, clean, modular code base is a great stepping stone to get you to a microservices style approach if you need it, if you need some of these benefits that microservices gives you. But unfortunately, I see lots of people jumping on microservices because it's cool. And that's fun for a bit. It's not the right reason to do this. If your monolithic code base is a mess now, jumping to microservices is just going to put a network in the way. It's a distributed big ball of mud you're potentially building. And that's not good either. So let's wrap this up. What am I trying to say here? Well, you need to think about aligning your software architecture with your code. These are just two views of the same thing. We need to bring architecture and code back together again. How do you do this? Adopt some sort of architecturally evident coding style. Think consciously about how you're structuring your code base, how you're organizing your code. Think about adding metadata into your code base. The reason I built this structurizer thing is because I want to auto-generate software architecture diagrams. I don't want to recommend in 2015 that we use Visio. This is stupid. Building architects do not use Visio. They use a modeling tool, and we should do the same thing. We should catch up, ironically, with the building industry. So the more information we put in our code bases, the more we can extract out automatically. What's the easiest piece of advice I could give you today to do tomorrow? Stop making stuff public. I see this in code bases. Everything is public. You ask somebody, why is this class public? The IDE made it public? That's an answer. It's not a very good answer. Lots of the frameworks we use tend to make things public by default. They tend to expect public things. Sometimes it's just muscle memory. I catch myself doing this as well. The last time I wrote some code, I wrote public class. Oh, no, it does not need to be public. Why are you doing this, Simon? It's just habit. And we need to break this habit. How do we do this? How do we break the habit? Apart from chopping your fingers off every time you do it, I don't know. But again, I can give you another piece of advice. Every time you do this without thinking, stick €1 in a charity jar. This will slow you down. This will get you thinking, is this class really a candidate for being public? Do I need it accessible across my entire code base? And my fun on it is very, very simply this. If your system, if your code base is hard to work with, you have the power to change it. Thank you very much. Perfect. Any questions then? Over here, yes.
What kind of tools do you use to generate diagrams from code?
I love this question. I didn't prime this. So what the question was, what sort of tools do I use to generate diagrams from code? And the answer is my own tooling. So this is exactly why I built some tooling to do this. So it's called Structurizer. It's a tool of two halves. There's an open source half. So there's a framework, a library built in Java on GitHub. And basically what it allows you to do is you write some code to describe a software architecture model. And essentially, it's an implementation in code of that systems, containers, components, classes thing I showed you before. So you write some code to describe your system, either manually or by scraping elements out of the code base using static analysis and reflection. That creates you a nice in-memory model. There's an exporter to JSON. You throw the JSON up to my structurizer.com web tool. There's a free plan you can sign up to, and it draws some pictures for you based upon the stuff in the model. If you don't want to use my tool, you can take the open source library. There is a dot file exporter, so if you're a big GraphViz fan, you can take the model and export it to GraphViz. There's a web sequence diagrams exporter, so you can take that model and basically visualize it however you want to. So that's the kind of long-winded answer to say don't use Visio. No worries. Question over here. So I had a slide saying a good architecture enables agility, and the question is, what makes a good architecture? And it's a really good question. And I guess for me, the answer is really around a clean structure, a modular structure, and a structure that's easy to work with. So a structure that when you want to add a feature, it makes sense where the feature should go. There are not lots and lots of options. You know, there's one kind of standard way that we do this. And for me, it's really about creating some nice module boundaries around our code. And it's all high cohesion, low coupling, Liskov substitution principle. It's actually all of Uncle Bob's solid stuff applied at a slightly higher level of abstraction. For me, that's what makes a good architecture. Right, and the other way around, when you need to find something, you know where to look. And that's why I go back to this maps concept. So what I'm trying to do is create a set of maps to navigate my code base. And one of the things I've done with my structurizer tooling is that if you link your components to some code, you can double-click a component on the diagram, and it takes you to the code on GitHub, for example. So I do want to create a set of maps that, the code is essentially street view, and then you want to zoom out to figure out where you want to get to. So diagrams as maps. Any more questions? Yes?
The benefit for generating code from the diagram
That's an interesting question. So the question is, do I see any benefit of generating code from diagrams? And the honest answer is no. We've tried this a lot in the industry. We've got things like model-driven architecture, model-driven design. It's never really taken off mainstream. There are definitely some applications where it works well and it's still being used. We've tried the whole drag and drop approach. So we create some sort of flow chart and then magically code gets created. They always never worked. Microsoft BizTalk, same sort of thing. I don't think this diagramming approach allows us to model the complexity that we really have in our systems. That doesn't mean it's not possible in the future, but I don't think we found a good way of doing it yet. Right, so it's a really interesting question. If you adopt a microservices architecture, surely you just get to the same situation where you have dependencies between microservices, and therefore you basically just get that spaghetti ball of mud thing happening again. And that's exactly the case. So if you take a very naive approach to adopting microservices, you do basically take all of your components, make them distributed, and have calls between them. If your calls are synchronous, you're exactly creating a distributed big ball of mud. The approach, I think, that the best approach is to decouple these things as much as possible. And for me, that's about looking at asynchronous approaches, asynchronous styles of messaging, eventual consistency, and these sorts of things. And that's a hard thing to do. And that's why, creating a good microservices architecture is hard. And it's not something we should just jump on blindly. It's the same design thinking, whether it's a bunch of services on a network or a bunch of components in a modular thing. You have to understand the boundaries and the responsibilities. Yeah. Yeah. If you've ever seen any of the diagrams that Netflix have generated from their microservice architectures, it's scary. It's basically millions of boxes with lines between them. And yeah, they have a lot of complexity there. So if you have two services, service A and B, and A depends on B, you need to either set up A, calling B, you need to set B up as well, of course, you need to mock out B, or you need to do a consumer-driven, contract-driven tests. So that's one of the other approaches people are taking to solve these types of problems. So it's a complex area. That's why microservices is not the silver bullet everybody thinks it is. All right. Yeah, over there. So the question is, we're adopting lots more parallel concepts, and asynchronous behavior and these sorts of things. And should we change our architecture diagrams to reflect this? And should we change our testing strategies? So we should definitely change our testing strategies. From an architecture diagram perspective, I think the static structure still stands. But at some point, I want to have a map of my static structure. But I also want some other views to describe the parallelism, the stuff that's going on. And actually, that's what Philip Critchen's 4+1 model is all about. He says there is a static model of your system. It's unfortunately split into logical versus development. But that process view is really where all that parallelism and asynchronous behavior lies. And I think that's the stuff that we don't often document sufficiently well. So if that's important, that's definitely a consideration.
questions, you can ask them later, definitely.
I'm all right. Thank you. Thank you very much. The rest of the day.